Okay, and then I will text you the link to this one.
I'll send it out to everyone. Thank you.
Yeah. Check, check. Woo.
Incredible.
Mm.
Oh my.
All right, so Chris, stand back up there so you can get the angle right.
Those angles.
That would be nice if it could be, well, be asking for too much to have it mirrored so that we can actually read it. Otherwise, I think it shows up in the mirror version, but that's okay. And then I'm gonna.
Is that good?
Yeah, that's good.
I'm gonna say hi to people.
Yeah. Put the brightness down so you don't have to look
yeah.
like you're staring at yourself.
Good.
Okay. Done. Oh, Peter. God bless you, sir.
Yeah.
Thank you so much.
Yeah, of course.
Okay. That's sent out. This is perfect. Woo!
I can I'll mute this.
It's just last first up here.
This is my last of,
I have some slides as well.
of the thesis different.
There's slides as well. You can take breaks on these. There's also water. Yes, great.
All right.
Here's some slides.
Oh, great.
We're all here. Thank you today to support Christopher Andrew Berkey as he defends his doctoral research. Chris is from College Park, Maryland, where he went to more or less.
More or less,
Close
yeah.
enough.
Maryland's
He did go to the University of Maryland.
That's right.
And did a bachelor's degree in material science and engineering. Like all of our admitted graduate students, he had a number of undergrad research experiences. I guess you built hovercrafts or control systems for hovercrafts. He even did some ALD work involving lithium air batteries, but then came to Stanford, interested in energy and the environment mostly, but has ended up working on the barrier function and mechanical properties of human skin, which is what you'll hear about today. One of the aspects of, well, two aspects of Chris's time here that have been remarkable is one, his ability to write. So in a research lab, we're constantly looking at publications and drafts of publications, and Chris's ability to write crisply and well is amazing. So as a result, he's now writing many of my research proposals, including one that is due, I think, in like this week.
Yeah.
In addition to getting ready for this, if you get any tough questions, you can say, well, I was busy. But the other thing has been Chris's ability and interest and dedication in mentoring students. So he has, in the time that he's been in the lab, mentored several summer undergraduate students, and some of those students have stayed on longer. And his involvement with them and helping setting up their programs and working with them has really been very impressive. So it's really something that's worth noting. Anyway, we look forward to your talk.
Thank you. Thanks for those kind words, Professor, and thank you to everyone for coming out to hear the defense. It really means a lot to me to get to share my research with all of you. And as you can see from the title, what we'll be talking about today are the effects of biomechanical stress on the barrier function of human skin. So just to give you all some background on the structure of human skin, it's very important to note it's a multi-layered structure. The topmost layer is human stratum corneum here. It's about 20 microns thick. Actually, this layer, although it's very thin, plays a critical role in the barrier function of skin. And part of that is because it's the outermost piece of skin that's coming into contact with environmental exposures such as temperature changes, solar radiation, and also any types of microbes or treatments that might get put onto your skin. Beneath the stratum corneum, or SC, we have the epidermis, which is about 200 microns thick. And beneath that is the dermis, which is 2 millimeters thick, and in the dermis is most of the vasculature of the skin. And you might be asking, why do we care about the biomechanics of the skin? It's actually a critical field of study for numerous applications, such as treatments and perception. We need to know how biomechanics of the skin are affected by different types of lotions or treatments. And also, changes to the biomechanics affect how we might perceive the action of these lotions. We also can quantify environmental damage by seeing how the biomechanical properties are degraded or changed. Additionally, biomechanics of the skin affect wound healing, and even the stress state of skin will affect how cells might differentiate and lead to the formation of scar tissue. And finally, of course, any types of wearable electronic devices that are in contact continuously with the skin, you're going to need to know how the biomechanics of the skin are affected by these devices. Or perhaps you have some device that might be sending vibration signals or something through the skin, and you want to know the biomechanics of the skin to make sure that device operates effectively and properly. So I want to zoom in. I mentioned the stratum corneum was very critical. I want to tell you a little bit more about that. The stratum corneum has a very unique structure, and it's kind of shown here. This layer is made up of corneocyte cells. These cells are surrounded by a very thick or robust protein envelope. And they're also, every cell is kind of riveted together by these protein junctions called corneal desmosomes, and these give the SC a very high toughness or cohesion. Two very critical components of the SC are the keratin matrix within corneocytes and the extracellular lipids. The keratin fibers are actually the main or even the only component within these cells because they've actually been, they're anucleus, they've kind of reached their terminal differentiation. They're about to be shut off. So there's not really any organelles or anything in these cells. And these keratin fibers are very hydrophilic, and a lot of water is stored in these cells due to hydrogen bonding to these keratin fibers. The extracellular lipids, kind of everything in between these cells, are mostly made of free fatty acids, ceramides, and cholesterols. And this forms a water loss barrier because these very hydrophobic lipids prevent water from just going out of your tissue immediately. And so this structure is part of why the SC is very good at preventing excessive water loss and also has a high cohesion, kind of prevents mechanical injury. Another aspect of the SC that you might not know is that it's incredibly stiff compared to deeper skin layers. Here we have a stress strain plot of full thickness skin. We see that its stiffness is only about 0.5 megapascals. On the other hand, we can measure the stiffness of stratum cornea. We see that depending on the relative humidity of its environment, it could be anywhere from 3 to 370 megapascals, which represents a 1 to 3 order magnitude of increase in stiffness. What this means is that whereas deeper layers such as the soft dermis are going to dominate macroscopic movements, such as, if I bend my arms, I'm able to do that without, pulling on my skin overly much. And any sort of local changes in deformations, such as if you have something that's tapping lightly on your skin, or if you apply a lotion and you feel some sort of tightness develop locally, that's going to be dominated by the extremely stiff stratum corneum, even though it is thin. I want to transition a little bit to talk about stresses and why we care specifically about stresses within the stratum corneum. First off, if you consider the skin in vivo, there's constantly going to be water diffusion in and out of the tissue, and maybe you have some cosmetic treatment applied that's also going to be diffusing. And there might also be some sort of environmental exposure happening. All of these have the potential to create stresses in the stratum corneum. And these stresses can possibly lead to mechanical damage to the skin. To quantify this, we can use a simple linear elastic fracture mechanics model shown here. And in this model, we have an important parameter called the energy release rate, G, which you can think of as the driving force for damage in the tissue. This factor depends on stresses, as shown here. And as stress increases, so does G. And at some point, a critical energy release rate will be reached. This represents the cohesion of the skin or its cracking resistance. Once G reaches GC, we actually can predict that there will be some sort of fracture event, such as cracking and chapping. And this is very detrimental to the barrier function, as you can imagine, because essentially now you don't have a barrier, and you have paths for microbes to get into the skin or excessive water loss to be happening. So one reason we care about stress is because it can cause mechanical damage. But even in the case where stresses might not be high enough to cause damage, another aspect is that high stresses could be perceived as pain or discomfort, especially if you consider that there are tons of mechanoreceptors throughout the skin. As stresses increase in the SC, these can actually be detected as they radiate strains down to some of these mechanoreceptors, especially those that lie closer to the surface between the dermal between the dermis and epidermis. Whereas high stresses might lead to feelings of tightness or discomfort, we can actually quantify the ability of lotions to then reduce the stress, which we can expect to be perceived as softness or comfort. So now with that kind of background, I want to now tell you what material I've actually been working on and doing my research on. And in fact, it is real human tissue obtained from cadavers, and this is what it looks like. But usually I'm working with the stratum corneum. And so to isolate the stratum corneum from full thickness tissue, first I will remove the subcutaneous fat, and then I'll place the dermis and epidermis in a 60-degree water bath for 1 minute. And this allows mechanical separation of the epidermis from the dermis. And then I'll take this epidermis and place it in a trypsin enzymatic digest, which will remove the viable epidermis, leaving only the stratum corneum that I can use for my experiments. So now let me outline the research that I'm going to present to you today, and that's all pertaining to stresses within the skin. First, I'm going to talk about an effort I've done to model drying stresses in the tissue, to really get at the fundamental cause of where are these stresses coming from. Then I'll tell you about different types of emollients, which is a form of cosmetic treatment, and about their ability to mitigate these stresses. And finally, we'll take a look at a type of environmental exposure, synergistic heat and UV damage from solar exposures that could lead to increased stresses, and we'll take a quick look at a way we can mitigate those stresses as well. So now moving on to talk about how I model these stresses, let me first tell you how I was able to measure the stresses in the stratum corneum during drying. To do this, first I would adhere a fully hydrated wet stratum corneum onto a glass substrate, and this had a reflective gold coating on the bottom of the substrate. While drying, the wet SC would lose water and stresses would develop, and there would also be an observable thickness decrease. The lateral stresses that develop in the SC are of a large enough magnitude to actually cause a deflection in this substrate. And by using a laser, we can actually measure this curvature change. By plugging this into Stoney's equation here, we can turn this curvature change into a stress if we just know something about the glass substrate itself. Here's what the actual data from these experiments look like. Let me walk you through it. In the first 3 hours, when we have fully wet SC, no real stress increase has occurred yet. And this is because we have essentially an oversaturated SC. It's been soaked in water. And so we're losing some excess water here. But really, the structure or the size of the stratum corneum is not changing yet. At about 3 hours, we start to see a dramatic stress increase begin to occur. We can actually quantify a maximum stress rate of about 2 megapascals per hour. Finally, at about 8 hours, we reach a plateau in stress, and this is when all of the water has been lost from the tissue. In this case, the plateau stress was about 7.5 megapascals. And I want to take a moment to highlight how large this stress is, considering the SC is a biological tissue. Typically, for softer tissues, we'll consider stresses in the range of kilopascals. So this kind of highlights the real importance of the SC, since it's dealing with these very large stresses due to its very high stiffness. It turns out if you then rehydrate the SC, you'll actually drop stresses back down to 0, showing that this drying process is completely reversible. And in fact, it's due to the presence of water. That's what this is showing. And so if you're like me, you're starting to wonder, why does the presence of water lead to, or why does the loss of water lead to stress? And you put water back in, the stress goes back down. And the question I asked was, can we actually fully describe drying stresses by considering the volume change due to water loss out of the tissue? So to probe this question, first I developed a model to actually describe water transport throughout the SC. I started with fixed second law, and using a separation of variables technique, was able to determine a very general solution to this equation using a linear combination of trigonometric functions as well as exponential functions. By including the boundary and initial conditions, I was able to solve the equation for our specific case. The boundary conditions I used was that the stratum corneum was a finite solid with a known thickness h. The glass substrate here was impermeable, so there's no flux past this substrate. Additionally, this surface concentration here was fixed throughout all drying, and this is a concentration we'll actually know based on the relative humidity of the drying environment that we can decide. Finally, the initial condition is that the entire SC is at a uniform concentration, C0. And this is a number we can actually get from literature for a fully hydrated stratum cornea. It turns out, though, if we're considering volume change, we don't really care so much about the dependence of concentration on X. We're more concerned about the total water concentration in the SC at any given time. So to solve for this, I integrated this equation from X equals 0 to X equals H. And this is the resulting equation here. And you see that this cosine term is now gone because we've integrated. What I want to point out about this equation is that this term in brackets here, as t goes to infinity, will just become 1. And so what this is showing then is that at t equals infinity, our concentration is expected to just reach the surface concentration, kind of showing that our boundary conditions are being met here. So the next step was to try to invalidate this water model to see if it actually matched what was physically happening. To do this, we used some data that was obtained by our collaborators from the University of Paris Sud, and they were doing Raman experiments on wet SC drying. Just as we measured the stresses, they were measuring the change in the Raman spectra. And by looking at the OH band, they found that the water content in the skin decreased during drying, and we were able to correlate that to the stress increase we observed. If you plot the data they saw over here, and that is the area of this OH band with respect to drying time, you see that our model plotted here in red somewhat well approximated the experimental data, but there was some significant divergence, especially at longer times. To deal with this, I considered that really there's not just one state of water in the tissue. In fact, there are 3 different states of water. And you can see this, but when you deconvolute the water band in skin, you can actually see there's 4 different peaks, 2 in the middle correspond to partially bound water. Let me explain kind of what these states of water are. First, there's bound water. And this is water shown here that's very tightly hydrogen bound to keratin fibers. And actually, even when you fully dry out the tissue, you don't lose any of this water. You can still see it in the Raman spectra. On the other hand, there's mobile water. And this is water that doesn't really sense the presence of SC components. And it's able to leave the tissue very quickly, and it has a higher diffusivity. Partially bound water is somewhere in the middle of these 2 states of water. And that is, it's sort of sensing the presence of bound water, but it itself is not bound by any SC components. It's able to leave the tissue, albeit with a lower diffusivity and a lower rate of diffusion. So instead of just trying to fit to the total water concentration, what I tried to do next was fit to individual mobile water concentrations and partially bound water concentrations. And you see right away, with respect to mobile water, now our model very well captures the behavior of mobile water as it leaves the tissue. On the other hand, this dotted line shows our first attempt at modeling partially bound water leaving the tissue. And this dotted line is using a constant diffusivity for the water transport equation. In fact, if you consider what's going to be happening with partially bound water as drying occurs, it's going to start taking on more of a bound water character. And that's because the SC is going to be contracting due to water loss. And it's already, this partially bound water is already sitting close to keratin fibers, and it's going to start having more and more bonds with these fibers. And so we'd actually expect there to be a decrease in diffusivity during drying for the partially bound water. So by allowing diffusivity to decrease sigmoidally with water concentration, I was able to fit the experimentally observed data very well. So after validating this water transport equation, the next step was to connect that to stresses within the tissue. We can start by considering the dilatation strain just due to water loss. If we consider the SC unpinned from a substrate, then as it dries out, we're going to have a strain in the X, Y, and Z directions. But since there's no constraints, the stress in the SC will still be 0. We can also assume that the strains in the X and Y direction will be equal due to the symmetry. But I'm allowing the strain in the Z direction to be different. And this is again due to that structure I showed you earlier of the SC, that it has these corneocytes that are somewhat disc-shaped, and they lie in the lateral direction. So now if we actually consider though our real case, where there's a glass substrate that the SC is pinned to, in fact now, because of these constraints, we have an elastic strain in both lateral directions occur. There's also a stress now in the lateral directions, and because of this stress, we have a Poisson contraction in the Z direction. And so then going back to this dilatation strain, before we could write it as just a sum of these simple drying strains in the principal directions. But once we introduce the constraint of the glass substrate, we would now write it in this way, because we want to think about the elastic strains if we're going to try to get towards the stress. Then we can use Hooke's law to now write down the strains in terms of their stress components as well as the elastic properties of the SC. After we do this, we can then just do some algebra to get stress onto the left side of the equation. We see that stress is now a function of this drying dilatation strain as well as the total thickness change, which we can measure during our experiments and fit for this equation. And also it's a function of these stratum-corneum properties, mechanical properties. Where the real magic happens is that we can now use the water transport equation I showed you previously to estimate this drying strain. And to do that, we're actually in this blue box here, essentially counting the number of water molecules that are lost at any given time. And then we can assign an average molecular volume to each of these water molecules. And by doing that, we can essentially sum up their contributions to the volume change within the SC. That's what this blue box is here. Then we would also subtract the total thickness change for drying, because this is saying that any volume change that could be accommodated by a thickness change, which is unconstrained, won't lead to stresses. And of course, there's also the mechanical properties of the SC here. And we allow the modulus to increase as drying occurred, which is observed in literature. So the next step then, we have our stress equations to see if it actually works or not. And you see it actually works incredibly well. In these open squares here, as an experimentally observed drying curve, the black line is what the model would predict for this tissue. And this is using parameters here that are all taken from literature. So we can have confidence in this fit. And the key here is to notice that it's really volume change that is underlying the increase of stress in the SC due to drying. There's not any sort of biological change happening in the tissue. It's actually just losing volume, and it's a mechanical effect. We can take this model a step further, though, by considering what's going to happen if we change the drying environment's relative humidity. So in this graph here, I've plotted points showing experimental measurements of both the equilibrium modulus as well as the equilibrium concentration or surface concentration of SC after allowing it to dry in various relative humidities. The lines here, the black line as well as the blue line, are showing the fits that I'm using to then input this data into this model here. So by inputting these fits and also allowing the thickness change to decrease when there's less drying, which is something, again, you can see from experiments, I was able to accurately describe drying in 3 different relative humidities, going from a very dry 5% to a less dry 45% relative humidity. Beyond just describing experimental data, though, we can start to predict how stresses will be affected by the relative humidity of the environment. And we see that there's actually this interesting exponential decay of stress here as relative humidity increases. And something that's very interesting is that once you reach about 70% relative humidity, the model doesn't really predict stress developing at all. This is indicating that there's actually a lack of driving force at these high humidities to pull water out of the tissue. And we can go a step further and quantify this driving force by considering the chemical potential of water in the environment above the SC. And if we consider that this atmosphere is a mixture of ideal gases, we can write the chemical potential in this way. And the activity of water will just be given by its partial pressure. Recall that partial pressure is dependent on relative humidity as well as temperature. So if we assume a constant temperature, we can just convert the relative humidity values into their chemical potentials. And we can then have the stress as a function of chemical potential. What's interesting is that over a wide range of RH values or chemical potential values, the stress depends roughly linearly on these factors. It's only once you reach very, very low relative humidities that you start to see a plateau reach, kind of indicating the sigmoidal shape of this curve overall. This is indicating that even if you have a very high driving force to take water out of the SC, there is a finite amount of water in the tissue. And so you can't keep losing water, you can't have stress keep increasing beyond this point. So this plateau would be expected based on the physical situation. Now I've shown you really how we can very accurately model the behavior of water in the tissue, and also we can connect this to stresses very accurately. The next question I had was, can we use this model to account for treatments, such as a commercial moisturizer? Can it go beyond just water? And so here we see this typical control drying curve. I rehydrated the skin, and then at this point here, I applied a commercial moisturizing cream and allowed the skin to dry once more. And we see that the main effect of this is that the peak stress decreased dramatically due to the presence of this moisturizer. And if we consider what's going on here, the hypothesis is that as water is leaving the tissue, treatment's also diffusing in. And so perhaps the main effect of these moisturizing treatments is just to replace lost water volume. And if you have a smaller volume change, you would expect a lower stress. So to test this, I did a measurement of the effect of glycerol on drying stress. Here we have the control curve, and we see again this expected effect of a reduced peak stress due to the presence of glycerol or glycerin. By modifying the stress equation this way, essentially allowing there to be a volume change in the glycerol, a thickness change in the glycerol, and a different effect on the stiffness of the SC due to the presence of glycerol, I was able to effectively capture this behavior and describe it just due to the new volume presence of glycerol in the skin. I used the same transport equation for glycerol, but I instead put diffusivities and changes to modulus and such that are taken from literature that we would expect due to its ability to soften the skin. So now I've shown you that we can create a very sophisticated model for water transport throughout the skin, and that really it's volume change that leads to stresses within the SC. And also this volume change accounts for stress, whether you're losing volume or if you're gaining volume, you'd expect a reduction in stress. What this naturally kind of leads to a new question, which is, I've studied glycerol here. Would this trend hold up for a wide range of emollients, or is there something special about glycerol? So to test this, I measured the effects of 14 different emollients on stress in the SC during drying. These are all shown here. If you need a little calibration on what an emollient is, because you haven't spent 5 years studying the skin, emollients are used to soften the skin, smoothen it, and they're often included in more complex moisturizers to enhance the spreadability of these creams. What I want you to notice here in this array of different emollients is that we have a wide range of molecular weights as well as chemical functionality. We have esters, ethers, as well as alcohols. And so what this will allow us to do is really see if it's volume that's having an effect, or if there's any sort of chemical function that actually would contribute to the stress change. To measure the saturation volume, or to measure the volume of these emollients in the SC, I performed the following experiment. First, I would take a piece of stratum corneum and I would measure its lateral dimensions as well as its thickness. I'd measure thickness in 4 positions, at least to account for the roughness of the stratum corneum to get a better volume estimate. After taking its volume, I would then take its mass, and then I would soak the SC in each one of these emollients for 1 hour. Then I would remove it, blot it clean with minimal pressure, and then take its mass again. And I would have a mass change here that accounts for whatever amount of emollient is left within the SC. By dividing by the density of these emollients, I could then obtain the so-called saturation volume of these emollients within the tissue. And then, as I said before, I also did drying stress experiments. And so on this slide, I've now plotted the results from the saturation volume study as well as the drying stress results. On the x-axis, we see the saturation volume in terms of percentage. of initial SC volume, and on the y-axis we see the reduction in peak stress that I measured using the stress experiments. And immediately you see a beautiful linear trend here with an R-squared of about 0.93. This is exactly what we would expect from this stress model. We expect that the stress within the SC would linearly depend on the volume provided by these emollients. I observed a secondary effect that I wasn't expecting though, due to the application of these emollients. And that is there was an increase in stress rate after applying the emollients. And we see that this increase in stress rate increases to about a saturation volume of 17% or so. And then it begins to drop back off. And so to figure out what's happening here, we need to consider the structural components of the SC that control water loss, since presumably an increase in stress rate means you're losing water faster. And so here I kind of zoomed in on the intercellular space between corneocytes and the SC. And you'll notice that the intercellular lipids are actually very highly ordered. And this is something that has been demonstrated numerous times using X-ray diffraction as well as electron microscopy studies. But there's a very highly ordered lamellar structure of the lipids within the SC. And other studies have shown it's actually this ordered structure that contributes largely to the lipids' ability to block water from quickly moving out of the stratum corneum. Since you must remember that all of these lipids are very hydrophobic, and that's how they're able to block water transport. So now if you consider that, in our case, we have several or very many emollient molecules kind of now residing in this intercellular space, all of these molecules are going to be disrupting the ordering of this intercellular lipid matrix. And it's very likely that this now allows new pathways for water to move through this intercellular space and out of the tissue without being blocked by the hydrophobic lipids. And this could explain why we see this increase in stress rate as more emollient is able to reside within the SC. To explain this drop-off, though, consider that as you get more and more and more emollients pushed into the SC, these molecules are often also very hydrophobic. And at some point, they might create their own barrier to water loss as they begin to saturate the SC more and more. And that could explain why we're seeing this drop-off with increased saturation volume. So then if you're like me and you see that saturation volume is critically important for predicting an emollient's effect on stresses in the SC, you might be wondering, is there any way to then predict the saturation volume if we know an emollient's structure? So my first pass on that is shown in this slide, where I plotted the saturation volume against molecular weight here and diffusivity here. Diffusivity was measured using time-resolved ATR, FTIR studies. And we see very rough trends, notably that saturation volume seems to increase with a lower molecular weight emollient and with emollient with higher diffusivity, which is something you might expect, because both of those you expect to increase the emollient's ability to penetrate the SC. However, there's a very evident scatter in these trends. So we might need another parameter to predict, the saturation volume of the emollients. So the next parameter I looked at was the so-called topological polar surface area. This was first described by Ertl et al. And what they showed is that while typically you might describe a molecule structure using complicated 3D software such as Carina, and then you could calculate its surface area and determine how much of that is polar. In fact, the contribution of polar functional groups is often, and then they showed this to have a very high correlation, is often a discrete number regardless of what the overall structure of the molecule is. And so then there's a very quick way to estimate a topological polar surface area, or TPSA, by essentially summing the contributions of the polar groups you have in the molecule. So I did this for all of the emollients, and then it turns out if you divide the diffusivity by the TPSA, you start to see a real trend emerge, showing that saturation volume increases with a larger diffusivity, and it increases with a lower TPSA. And you would expect that because a lower polarity emollient could better penetrate these hydrophobic intercellular lipid barrier. We can actually improve this fit a little bit more if we include the molecular weight here again. using the same dependence you saw before. But what I want to emphasize about this is there's still a lot of work that needs to be done in this area. And there might be other parameters that are controlling the saturation volume, the ability of emollients to penetrate the skin. And also consider that really, the diffusivity, you would expect it to also depend on polarity and molecular weight. And so what we'd really like to do is eventually find the independent constants and parameters that are really controlling saturation volume, rather than having this relationship here where things might be depending on one another, and we're not really getting to the core aspects of the molecule that are determining its ability to penetrate the SC. So now I want to change gears a little bit and talk about this environmental exposure of synergistic heat and UV damage from solar radiation. Well, we can think about it in this context. So this environmental exposure is going to be something that's increasing stresses, as we'll see, and leading to damage. On the other hand, the emollients here are something that's mitigating treatments that can reduce stresses in the SC and prevent damage. So really you can think of these as going kind of hand in hand, where we want to make sure we can understand how stresses are being increased by the environment so that we can start to develop treatments that can reduce these stresses and prevent damage. So to calibrate everyone on the details of solar irradiation, I've included a standard plot of the irradiation spectrum of our sun. And you'll see that there is a characteristic or expected peak here in the visible region, showing that we're mostly getting visible wavelengths from the sun. This is why we can see with its light. There's a long tail here in the infrared region, and then there's a actually very steep drop off in the UV region. And what might surprise you is, with all the talk of preventing UV damage, it's actually a very small percentage of the total solar spectrum. And the reason we care about it, though, is because these are much higher energy wavelengths, and so they're more likely to do damage. We've actually quantified the effects of UV damage on stresses previously, and we see that the peak stress is significantly increased. And also we have a very dramatic increase in stress rates due to UV exposure. This here is the control curve, and the UV exposure happened here before we allowed drying. And just to remind you, the reason we care about increased stresses due to UV damage or solar damage is that these stresses can lead to painful cracking, chapping, mechanical damage. But also, even if there's not noticeable damage, you also will feel these tensile stresses as pain or discomfort in your skin. And so the question that I was asking is, we've looked at these UV wavelengths a lot in the literature, and I've looked at them previously. Is there anything being done by the rest of the solar spectrum that makes up, a large part of it? So to study this, first I measured the absorbance of various skin layers across many wavelengths. And to do this, I used a light spectrometer equipped with an integrating sphere. And this was useful to capture any sort of diffuse reflectance or transmittance that came off of the SC, so I could just measure its absorbance of light. And what we see is, interestingly, there's actually almost no absorbance of IR wavelengths by the SC, whether it's hydrated or not. In fact, it's really the dermal layers, or even the epidermis to some extent, that are absorbing IR wavelengths. And this is quite apparently due to the high water content of these tissues. And so you might initially think, well, if it's not absorbing these wavelengths, maybe IR is not doing anything at all. But what I'd urge you to consider is that as the dermal and epidermal layers are absorbing IR light, they're going to start heating up. And so to measure this effect, I use this infrared camera that you can attach to an iPhone. I measured my skin temperature as I stood in sunlight. And we see, yeah, it's real experimental method. And we see that there is a significant increase in skin temperature due to sunlight, due to sunlight hitting your skin, of about 4 degrees Celsius. And so, while this SC might not be absorbing IR light, and there might not be any sort of photochemical reactions happening from this low energy wavelength, it's very likely being heated up by the absorption of IR light of deeper layers, and then this heat will conduct to the SC. So to measure the effect of heat on the SC, and specifically we wanted to measure is the heat amplifying UV damage, I performed stress experiments on skin that was exposed to UV at a variety of temperatures. And that data is shown here. On the x-axis, I'm plotting the time of exposure to UV or combined UV and heating. Up here on the top of the plot, I've put sort of milestone markers for how much UV dosage you have at the times I use for the experiment. On the y-axis, we have the normalized peak stress. So 1 is control, and anything higher than 1 means we have an increase in peak stress. And immediately you'll see, because of this giant arrow I've drawn, that we have a very large increase in peak stress due to combined heat and UV damage. And we actually see that it really is combined heat and UV that leads to the largest peak stresses observed. I also looked at the change in normalized stress rate. And we see here that heat doesn't really change the effect of UV, but UV is dramatically increasing the stress rate. If you're wondering, is this really a synergistic effect or is this just an effect of the heat? I also measured the effect of simply heat exposure without UV on the stresses. And we see that heating does increase stress somewhat, but nowhere near to this level. And additionally, in terms of stress rate, heat has almost no effect on stress rate. And so we're able to see that really it is actually a combined synergistic effect of heat amplifying UV damage that's causing these increases in stress. And we can think about what's happening to the skin during irradiation that's actually leading to these noticeable stress effects. So to start out, we'll look at the simply heat-exposed skin. And one thing to note is that there's actually a phase transition of the intercellular lipids at 35 degrees Celsius. And this transition is from an orthorhombic densely packed structure to a hexagonal less densely packed structure. And if you recall our discussion previously about the critical role of these lipids in preventing water loss, it's easy to see how a less densely packed lipid arrangement will allow water to leave the tissue, a greater amount of water to leave the tissue. In fact, other studies have been done measuring total epidermal water loss, TEWL, plotted here against SC thickness containing alpha phases, and these alpha phases are these orthorhombic phases here. And they show that as you, Damien and Boncheva showed that as you reduce the concentration of these orthorhombic phases, you have a much larger total epidermal water loss. And that could really explain why we're seeing an increased stress here. In order to understand the UV effects on increasing peak stress, I performed my own Raman spectroscopy studies on the skin before and after UV radiation. And one of my key findings is that this CH2 twisting peak that details the lipid Gauss-trans ratio, I saw that this peak shifted to higher wave numbers after UV irradiation. And in fact, I saw this for all UV exposure conditions. We had an increase in the wave number, the position of this peak. What this means is that UV is actually causing our lipids to transition to a Gauss state. And here I kind of included a picture of the trans state of lipids and the Gauss state with these kinks. And it's easy to see how if you have more lipids transition to this Gauss state with all these kinks, it's going to be much harder for these lipids to arrange into their very ordered lamellar structure. And so as you lose that lamellar order, we would expect greater water loss and increased stresses as a result. And finally, we can also think about this increase in stress rate. And again, I performed Raman studies and found that in fact, it's actually changes to the keratin structure as seen through the amide 1 band that correlated with these changes in stress rate. Notably, by deconvoluting this amide 1 band into 4 separate contributions, I saw that the amount of alpha helix keratin decreased, whereas the amount of beta sheet keratin seen here increased. And I saw this again for all exposure conditions, whereas heating had little effect. The reason this transition of keratin from an alpha conformation to more beta sheet conformations could be allowing faster water loss is if you consider that the tertiary structure of these proteins is highly dependent on the relative concentrations of these secondary conformations. And remember that we have a lot of water stored right next to these keratin fibers. And so it's entirely possible that as we're changing kind of the order of these large proteins, we might be shifting the concentration of bound water to more partially bound water, thus allowing water to be lost at a faster rate from the tissue. So now to wrap up my defense, I wanted to show you an example from everyday life where several of these effects I've described to you over the last hour can be happening simultaneously. And that's the effect of a combined exposure to a sunscreen or photoabsorber, as well as UV radiation. The photoabsorber I'm looking at is this DOMBM shown here. And so we see there's this typical control curve, but if you just apply DOMBM, you see this drop in peak stress. And this is actually reminiscent of the effect of emollients on SC stress. And so we can see that actually the DOMBM is having the emollient effect, taking up lost water volume, and thus reducing skin stress. In red here, you see the typical UV damage effect on SC stress. What's interesting though is this purple curve showing both UV exposure as well as the presence of DOMBM in the tissue. And here we see that this stress is still reduced compared to control stress, which is good news because that means you're not going to perceive this as tight or damaged, and you're not going to have any sort of mechanical damage happening. The reason it might be increasing somewhat though is because actually this DOMBM is not completely photostable, and there is a reduction in its concentration as it absorbs UV light. And although this is a smaller reduction in its concentration, it's still allowing some UV damage to occur, raising the peak stress here. And so what I want to emphasize in this slide is that really you need to be able to understand the effects of emollients diffusing into the skin, water diffusing out of the skin, as well as UV damage or any sorts of mitigating treatments like sunscreens on stresses in the stratum corneum, if you want to be able to capture what's happening in everyday life and then design treatments that could prevent this damage and keep the skin healthy. So just to conclude, remind you what we went over. I showed you that we have now a very detailed water transport equation that can model water loss, and we can connect that water loss to mechanical stress by considering the volume change due to water loss. And then I showed you that with a wide range of emollient molecules, we can actually see that this expected model, the expected effect of volume increase from the model holds up with a multitude of these different chemical structures and molecular weights. And I detailed a little bit kind of how we might be able to predict this saturation volume, but further work needs to be done. And finally, I just showed you the ability of synergistic heat and UV damage from solar radiation to amplify stresses in the stratum corneum. And we talked a little bit about ways we can think about protecting that with sunscreens. So now, before I close and ask for questions, I just want to take some time for some acknowledgments because a PhD is not done alone. First and foremost, I want to thank Professor Jaspar. Rainer, you've been an incredible mentor to me and taught me so much about being a researcher, but also just about how to be a more mature person. I really appreciate that from you. I came to your lab as a young guy from undergrad, and look at me now. I also want to thank Professor Allison Okamura, the chair here. Professor Okamura, we hadn't met in person before today, but at numerous poster sessions, we've actually been positioned next to your group, I guess, because we both kind of work on skin science. So kind of see your work, and I think it's incredible, and I'm glad you can have some input on this work. Professor Hallstrom, thank you for being on this committee. You were actually the first professor I did research with at Stanford, so I briefly rotated in your lab for a quarter during my first year. And thanks to you, I got to see what a real bio lab would be like, and that's a very valuable experience. Professor Eric Apple, thank you for also serving on the committee, and thank you for the advice you've given me outside of academia and the mentorship you've given me. Professor Chad Hurry, I've had the opportunity to take your biomechanics class and learned a lot from that, especially about the deeper skin layers And I thank you for that knowledge and feel that you're here to be able to get input on this work. Of course, I had many collaborators that I worked with from industry, and they contributed a lot to this work. I want to thank Annette and Marcus from BASF for working with me on the emollient studies. Nozomi and Kazuyuki from Shiseido in Japan helped a lot with the sunscreen and then synergistic exposures. And Andrew Watson and Paul Matz really were great collaborators during the PhD as well. Of course, I'd be remiss if I didn't thank all the staff in the material science department as well as Stanford as a whole, especially Carol, Yusong, Gavin, and Mara. I often would just walk in and say, I don't know what I need to do for this form, that form. Can you please help me? And they were very patient with me and walked me through what I needed. I'm thankful to Tom, Jeff, and Carl Hines, who helped me produce a lot of the substrates that I used in this work, and also thanks to Jeff for his incredible running of the SMF laboratory on campus. Of course, I'm also so thankful to the Dowscar group. This PhD would not have been the same without you guys. Just constant discussions and really fun group meetings and fun outings. I'm so thankful to all of you, and especially thankful to the SC subgroup members who knew you could have so much discussion about skin and then not really get bored of it. Also, thanks to these summer students I was able to mentor, as well as adjunct faculty member Bob Miller, who was very insightful when trying to figure out the action of these emollients on the skin and the lipids. I also need to acknowledge, my church community and all the friends that have supported me throughout the PhD. So many great memories of my time here at Stanford. I'm so thankful to all of you, and yeah, it's just been incredible. So thank you so much for your support and for so many of you for coming out today also. And then last, but certainly not least, I need to thank my family and especially my wonderful wife, Chelsea. Chelsea, you've been incredible supporting me for the last couple months as we've been ramping up to the defense and in the time before that too. Thank you so much. Love you very much. And also my family, they raised me and they're been the best support network throughout my life. And none of them could be here today, but several of them will be here for graduation, and I'm very excited to celebrate with them and thank them in person for all they've done for me. So with that, I'd like to close and ask for questions. Thank you for your time.
So as part of the open session of this exam, questions?
Yeah, Ross.
So on your UV exposures, there's some pretty high energies. Do you have a justification for that?
Yeah, that's a great question. So we looked at a range of dosages. And the reason for that is we wanted to get the kind of full damage curve of energy exposure onto the skin, so that we could have like an accelerated test of these high dosages, see what the maximum damage was, and we could kind of back out what would happen at lower dosages. Another thing to consider is that actually, since your SC doesn't refresh completely in a day, it takes maybe 2 to 3 weeks, you're actually going to be accumulating some damage over time, over multiple days of exposure. And so you might get to higher exposures than you might expect from a single day.
Great talk. I wanted to, so the kind of rehydration effect was really impressive at the start. Do you see any effective cycling that? So after several drying and rehydrating cycles, does that effect lessen?
Yeah, so actually, Jacob Bowe, the previous student to graduate from the SC group, really looked a lot at rehydration. He saw it was very reversible over, I think he went out to 4 or 5 cycles and there was still perfect reversibility. He would actually measure stresses during rehydration and found that rehydration would occur actually much faster than drying, which is interesting, and it's good to know because it means that our skin kind of wants to be hydrated and be protected. And so I would encourage you, I can give you his email if you want to learn more, but yeah, it is reversible. Yeah.
If you could just finish his publication.
If you would just finish his publication. He's got a few. Yeah.
How does the
water transport rate between the epidermis and the SC compared to like the SC in the atmosphere? On your first slide,
Yeah.
like glass for the
Yeah, that's a really good question about the substrates in particular. So often when you're considering, in vivo, you'll typically think of the dermal layer especially as kind of a water reservoir because it's got just water from your body that's constantly in contact with it. And so really we think of SC as sitting on top of this, effective pool of water if you're just thinking about the water effects. And so if you're at a very dry humidity, you're actually going to have a very severe concentration gradient throughout the SC of water continuously. And then at a lower humidity, at a higher humidity, that's going to be a much more constant gradient. And that's sort of what we're assuming by starting at a fully saturated SC is that we have, in vivo, someone's in a very humid, moist environment. There's no concentration gradient through the SC. And then when we put it into the drying environment, in our case, we start to have that concentration gradient, just like you would have in the in vivo case when there's a large concentration of water deeper in the tissue.
When we were going over the water transport model, you had the sort of graph that was deconvoluted into 4 different peaks for like bound to
Partially bound.
Yeah, so there are 2 peaks for partially bound.
That's right.
On what those 2 peaks were.
Yeah.
There are 2 peaks versus just that.
Yeah, right. So consider in Raman, you're really probing the bonding between atoms, right? And so when you have the water molecules in there, you're kind of probing the strength of the hydrogen bonds that they're forming with different SC components, or with themselves in the case of mobile one. And so it's possible that you have maybe partially bound with just a single hydrogen bond, or maybe you're partially bound with multiple hydrogen bonds, and that could be leading to these different peaks. But really, it's just that there are 2 separate binding states of water in partially bound configuration that still have this very similar transport properties. So if you plot them, you'll still see the same.
Can you go back to a slide like halfway through the second to last
Yeah.
section?
What slide is that? Halfway through the second section.
Yeah, like
This slide?
it was the slide that had the experiment over time, and it had like it went up and then down and then up again with 3 different.
Do you mean this?
That'll work.
Okay.
So,
Okay.
so I guess I'm not sure if I fully understand what this experiment was doing. So you dried it out once first for the control, and then you rehydrated it, and then dried it out again with the commercial moisture.
That's right. Yeah.
So why did you have to? Did you always do the control thing?
That's
first?
right. Yeah, that's right. And this actually raises a very important question. That is, are you always going to expect exactly 7 megapascals for every piece of skin that you measure? And the answer is no, you will not. And that's why you need to do a control every single time, because there's a wide, diversity of skin, and so everyone's skin is going to behave a little differently. But there are very well-known ranges of these properties that you'd expect for different types of skin. And so all the skin that I measured in this work or worked with was from female Caucasian donors, and it had the same phototype. And so that's one way we minimize this biodiversity, but another way was to just continuously take a control measurement of each piece so that we could really compare apples to apples when we tested the treatments.
Okay, so it's kind of normalizing.
Yeah.
Okay,
Exactly.
so then when you had the graphs with three things in the second.
Yeah, so that's, I think you're thinking of the last slide.
Oh, really?
You're thinking of this slide?
Yes, that's
Yeah,
the
that's the
exact
last
one.
Yeah.
So
Yeah.
the blue, purple, and red were from different populations of samples.
Yeah. So really there should be 3 control curves here, but what I did was I normalized all the stresses here. So all the stresses are going from 0 to 1. So they've all been divided by their, peak magnitude of stress. And so that's how we're able to compare in this case by saying, there's a 20% increase due to UV, there's a 40% decrease due to this DOMDM. And maybe more than you'd expect. By normalizing this way, you really can compare different pieces of skin. It's actually quite incredible. I'm very glad for that because it would have messed up the research. You couldn't do that.
Yeah.
But in fact, you can compare, percentage changes in different pieces of skin, and they're usually very consistent.
How big were the kind of standard error of the mean bounds on these things? Was it like 2% variation on those curves, or was it
So I
like?
have an example of that in the case of the emollients, and it is maybe 2 to 5%. So here I plotted the reduction in peak stress on the y-axis, so you can sort of get an idea for its size. And in some cases, it's very low, especially at this, this treatment had incredible reproducibility. Sometimes it's a little bit higher, but it's about this.
Well, this is great. My 40s. This is a
Yeah.
inviting you all to the close session. Let's thank Chris very much.